This course takes you from the basics to the advanced practical applications of fine-tuning large language models. Tadev teaches this course. She is an industry leader and CEO of LunarTech. You'll start by understanding what fine-tuning is and how it differs from pre-training and prompt engineering. Then you will learn about hands-on methodologies, including supervised fine-tuning and reinforcement learning with human feedback. The course also includes a deep dive into parameter-efficient fine-tuning techniques, specifically QLoRA, a revolutionary method that allows you to fine-tune massive models like Llama 70B on a home workstation. Through practical end-to-end case studies using Python, PyTorch, and Hugging Face, you will move from theory to implementation.
Hi there. In this course, we are going to take you from the basics to advanced practical applications. You will discover what fine-tuning is, why it matters, and how it differs from pre-training, prompt engineering, retrieval augmented generation, or RAGs. We will break these concepts into clear, digestible lessons that set the stage for hands-on experimentation. I'm Tatev Vaslayan, co-founder and CEO of LunarTech. With bachelor's and master's degree in econometrics and operations research, so advanced mathematical and statistical degree from Erasmus University Rotterdam, I bring more than 7.5 years of real-world experience with Fortune 500 companies from data science, data engineering, and AI engineering. And I've led multiple tech organizations in Italy, the Netherlands, in San Francisco, and more. I've worked on high-impact projects as a leader and as a hands-on developer and AI engineer. Worked on groundbreaking research, published scientific papers in NLP, AI, and data science to make AI accessible to everyone. Over the next few hours, we will talk about step-by-step through the fine-tuning process. First, you will learn the underlying methodologies: supervised fine-tuning, semi-supervised fine-tuning, and reinforcement learning with human feedback. Next, we will dive into the specifics of fine-tuning. We will look into the Llama models, fine-tuning of such models, how to prepare your instruments, curate your data, and set up your hardware and code environment. The highlight of the course is our deep dive into the parameter-efficient fine-tuning techniques. We will explore QLoRA, which is basically a combination of quantization and LoRa, a method that lets you fine-tune powerful models like Llama 70B on home workstation. No billion-dollar setup required. If you are ready to elevate your tech skills and dive into one of the most transformative areas of artificial intelligence and generative AI, join us. This course is more than a theory. It's your ticket to mastering the tools that are reshaping our world. For those aiming to become a master and professional in AI engineering, our newly launched AI Engineering Bootcamp is now open for applications. In just 6 months, you will master the machine learning and deep learning advanced topics as well as the one of generative AI, like large language models. You will build your own large language model from ground up, pre-training and fine-tuning, complete real-world projects using state-of-the-art tools, wherever you feel comfortable learning. Use the link below to apply and ignite your future as an AI leader. So, without further ado, let's begin your journey to fine-tuning excellence. Welcome to the course on fine-tuning large language models. So this is the module as part of our comprehensive large language models course, and in this module we are going to dive deep into the fascinating world of fine-tuning, a very important technique for tailoring large language models to specific tasks and improving their performance. So this is going to be an involved module as part of our comprehensive LLM course, and we are going to explore a whole bunch of topics to form a clear and picture-perfect idea of what fine-tuning is and how we can do it. So we are going to combine the theory with practical implementation, and at the end of this module we are going to conduct an end-to-end case studies where we will use the PyTorch and then also TensorFlow and many off-the-shelf pre-trained large language models from Hugging Face in order to fine-tune them. So in this module, we are going to discuss what is the fine-tuning. We are going to formally define it, where it is allocated in our food chain of LLM development. We are going to talk about the pre-training versus fine-tuning. So we'll compare the two processes. And then we will talk about prompt engineering versus fine-tuning. What is the difference between those two? Then we will talk about the fine-tuning as a task. So what does fine-tuning actually do to the large language models? And then we will talk about the benefits of fine-tuning a large language models. Then we will talk about the step-by-step guide. So we will give clear step-by-step process for you how you can fine-tune a large language model. Then we will talk about different methods for fine-tuning large language models, because there are varieties of techniques and approaches you can use when fine-tuning a large language model. So we will clarify that all. Then we will talk about this distinction and differences between supervised fine-tuning, semi-supervised fine-tuning versus the reinforcement learning with human feedback. So those different sorts of fine-tuning techniques. Then we will talk about 3 options for specifically parameter fine-tuning. And then we will talk about parameter efficient fine-tuning, PEFT, very popular technique for fine-tuning large language models. And finally, we will talk about one of the most infamous fine-tuning techniques that you must know if you are preparing for a career in AI engineering, and specifically in generative AI and large language models, which is the LoRA. So low-rank adaptation for fine-tuning large language models. So in this part of the course, we won't yet dive into the QLoRA, which is the quantized version of LoRA, but we will lay the ground for that too, because for once you understand the LoRA, and in the next module, once you also understand the quantization, then we can combine the two, quantization and LoRA, in order to understand QLoRA too. So in this module, this is what we are going to cover. This is going to be an involved module, but at the end of this, you will know entirely this process of fine-tuning large language models as a pro, and you will also do it by yourself by implementing the learn theory into practice in Python. So without further ado, let's get started. So welcome to the first part as part of our fine-tuning LLMs module. We are going to explore this interesting world of fine-tuning large language models like the ones of GPT-4, Llama 3, Llama, etc. So our journey today will help us to understand why fine-tuning is important and not just beneficial, but very important for specialized applications. So by the end of this session, you will not only learn the theory behind fine-tuning, but also experience the hands-on by comparing the fine-tuned model to non-fine-tuned models. So let's talk about the fine-tuning and where it is allocated. So fine-tuning is the step that comes right after the pre-training. It is an optional step, but highly recommended because it is not just beneficial, but crucial for specialized applications. So fine-tuning is really important for adapting a generalized model to perform specific tasks with higher accuracy and efficiency. Whether you are a developer that is creating a chatbot, a code completion tool, or a sophisticated AI for interpreting medical data or low data, fine-tuning allows your model to excel in niche that it serves. So it's a powerful technique to enhance the performance of these general purpose language models like GPT-3 and GPT-4, which are pre-trained models. So we've seen this visualization before when we were looking into the life cycle of large language models. We saw the pre-training, then the second stage, the fine-tuning, then we saw the prompt engineering and the regs. So in this life cycle of these advanced language models, the large language models, there are the several key stages like the pre-training, fine-tuning, prompt engineering, and regularization, where the fine-tuning comes right after pre-training. So we learned that pre-training involved the training of the model on this very large, super large data to learn the general language patterns. We even compared this to this idea that the child goes to the basic school and then to the high school and learns a whole bunch of fundamentals, a large amount of information. Then the fine-tuning is basically this process of helping the child to specialize in a certain area. let's say the child or the student graduates from high school and then they need to choose a university, or let's say bachelor's degree in mathematics or bachelor's degree in arts, and then specialize in that area of expertise, meaning that then they will be exposed to more specific sort of information. Similar thing is happening with the fine-tuning. Think of the stage like taking this very basic model and then specializing it in a specific area of expertise. Think of this stage of going from pre-training to the fine-tuning as in the very beginning having this rough diamond. It's valuable but not yet tailored for a specific task. That's the pre-trained model. And then the fine-tuning is this process where we take this rough diamond, we polish it a lot, and then we are enhancing its capabilities for specialized applications. So it becomes much more beautiful, it's more shiny, more fancy. And that's basically when we go from pre-training to fine-tuning. We are trying to address these shortcomings and we are trying to specialize the pre-trained model into the specific tasks. And then the model is tailored for performing these specific tasks. That's basically the fine-tuning. So, for example, to illustrate the impact of fine-tuning, let's compare a base model, let's say this pre-trained model. It can be any model like GPT, GPT-3, GPT-4, or Llama, anything in the pre-trained stage, not yet fine-tuned. And then this is the left-hand side, what we are referring as base model, and in the right-hand side, we have the fine-tuned version of that model. Imagine we have this chatbot that is powered by this base model in the left-hand side, and we are asking to the model, what's your name? Then the base model might respond the same. What's your name? Essentially parroting the input. This happens because the model has not been yet trained on a specific task for understanding and then responding appropriately to such questions. So the model is not yet able to understand that when someone is asking, what's your name? They, instead of repeating, they need to understand that this is a question, and then they need to perform this task of answering a question and then come back with an answer like, this is my name, for example, Adhev, and this is the answer to your question. So essentially, in the base model, the model is not yet sophisticated enough to perform the task, the specific task of understanding and then responding to such question. Now consider the right-hand side model, which is fine-tuned to a specific task. So when we are asking to this chatbot that is based on a fine-tuned model, what's your name? Then the fine-tuned chatbot will respond, well, my name is Lunar, and I'm the chatbot of LunarTech. So this significant improvement that you can see, the base model versus fine-tuned model, is the result of fine-tuning a base pre-trained model, where the model has been trained on a smaller, specific dataset to better understand and generate responses that fit the context. So it understands that there is a question that is being asked, and also it understands what kind of questions is being asked, and also understands how it should answer. My name is Lunar, so provides its name, and then the chatbot of LunarTech. So that's the idea behind the fine-tuning, at least at high level with this example. Let us now formally define what the fine-tuning is. So fine-tuning is about adjusting a pre-trained language model to excel at a specific task. So this means that we take an existing pre-trained model, for example, GPT-3, or it can be also GPT-4, Llama, Llama 3, anything that you want as a pre-trained model, and then further train it by tweaking its internal parameters. These parameters are like the model's brain connections, and by adjusting them, we can change how the model behaves and what kind of output it produces. So let us unpack this definition. So what do we mean by tweaking the internal parameters? Well, we know from deep learning, but also from the pre-training process that we discussed as part of this course, that the way large language models are pre-trained is that we are using this transformer-based architecture, depending on what kind of model we are dealing with, whether it's decoder only, or the main encoder and decoder sections, or specific LLM. And then we are continuously training this model to optimize the model performance. We are using all sorts of techniques with the one goal to end up with a set of weight parameters and bias parameters that will result in the lowest loss for our model. because this means that our model has high accuracy and is able to understand the language and also process the language in a meaningful and accurate way. So this end result, when we are getting this whole bunch of billions of weight parameters and bias parameters, they are the internal parameters of our large language model. And when we are performing the fine-tuning, it means that we are taking this base model, where base model is basically a file that contains these different parameter values, the weight values and then bias values, and we are adjusting them. So we are adjusting these weight parameters and bias parameters slightly, such that we can change how the model behaves. Because in the pre-trained stage, the values that we are getting after pre-training the LLM, these values, they represent this so-called brain connections. It's like in our human brain. So we know exactly how we need to do things thanks to our brain connections and our neurons. If we tweak them and adjust them artificially, then the way we will respond will be different. So once we start to get more information, more specific information, and we'll learn a bit more, we start to also respond to questions differently, right? In the same way, we need to also adjust these parameters that control the way LLM works, such that we can change how the model behaves, how the model understands the tasks, and how it answers those questions, for example. And that's exactly what we do as part of this fine-tuning process. We take the pre-trained model, the weights and the bias parameters that is provided from this pre-trained stage, and then we need to perform once again a training process to adjust this weight and bias parameters a bit, such that the model will start to behave like we want it to be on a specific dataset and for specific tasks. So at its core, fine-tuning involves continuing the training of a pre-trained model on a new, often smaller dataset with specific characteristics. This process adjusts the model weights to better reflect the nuances and these different idiosyncrasies of the target domain or task. So what do I mean in here? So it means that we basically have the pre-trained process when we are training our large language model on a very large general data. It doesn't contain specific data, but it does contain general information about different sorts of areas of expertise. But when we introduce this specific data, then we need to once again train our pre-trained model such that the model will learn to excel in that particular area of expertise. And once we are done with the second stage of training of our LLM, then the model is called a fine-tuned model. So when we talk about these weights in the context of fine-tuning, we are referring to these internal parameters of the model once again. So these are the weights that determine how the model processes the input data and generates the output in exactly the same way as we do in the pre-training. So in both cases, the internal parameters and the weights, we are referring to these weight parameters that we have both in the pre-training process and in the fine-tuning process. So during the fine-tuning, we just need to adjust these weights that we got from the pre-training final stage to change them a bit to improve this performance of the model on a specific type of tasks and in a specific area of expertise, making it more accurate and more efficient. So that's the idea behind this fine-tuning. And the idea is that, if we illustrate it with this figure, is that we take the base model, that's our pre-trained model, we add more data in a specific area of expertise. And when we add this more data to it, then we are able to once again train our pre-trained model in this specific niche and obtain a fine-tuned model. A fine-tuned model that is now able to better perform those specific tasks in that specific area of expertise. Let us actually look into a couple of examples to make this entirely clear. So think about the process of a person becoming a doctor. Consider this medical professional who begins with their general medical training. I'm sure you know that it takes many years for a person to learn all sorts of things that helps them to become a doctor, starting from biology to anatomy, genetics, but also to understand these different diseases, because a doctor, independent what kind of specialization they will have, they need to have this fundamental general training and knowledge. So once they decide to specialize, they can decide from these different specializations, like we do with our fine-tuning. We want the model to specialize. So once the doctor has gone through this general training, medical training, and they learn all the fundamentals in place, then they are ready to specialize. They can decide to go into the cardiology, specialize into neurology, oncology related to the treatment of cancer and diagnosis of cancer, to become a pediatrician, orthopedics, dermatology, endocrinology, to specialize in the hormones and then endocrine glands, etc., or gastroenterology, hematology, all sorts of specializations in medicine. So if they, for example, decide to specialize in oncology, their training will narrow down to focus intensely on cancer treatment, the latest research in oncology, to look all sorts of papers that have been published about these different cancers, etc., how they can be diagnosed, how they can be treated, these different specialized treatment protocols they need to know and be aware of, or the experimentations, etc. This focused expertise will allow them to provide more specific and better care and specific treatment plan than general practitioner might offer. For instance, when we have two different models, one is the base model, the other one is a fine-tuned model that we have fine-tuned using the base model, but then combining this with a specific oncology-related data. When we ask this first base model, what should I do about this unusual mole? Then the answer would be, well, keep an eye on it, and if it changes color or the size, consider visiting a doctor. So it kind of provides you this general answer, not specific, and is not also very helpful, right? And then we have the fine-tuned model, so-called oncologist assistant or chatbot. And it says, well, it's important to monitor for the ABCDE signs: asymmetry, border irregularity, non-uniform color, diameter larger than 6 millimeters, and then evolving shape and size. I recommend scheduling a dermatology appointment immediately for potential biopsy to rule out melanoma. So you can see this difference between general practitioner versus oncologist. And the same also holds for our chatbots. One is kind of the general practitioner, our general base model that is just pre-trained on the general amount of text, large amount of text for general tasks, versus the fine-tuned model that has been fine-tuned using a large amount of specialized oncology-related and dermatology-related data. So you can see the answer's difference. You can see how helpful the answer from fine-tuned model is versus how unhelpful the answer from the base model is. And that's the power of the fine-tuning. So let us actually look into another example. Imagine that you have a law student who has been trained broadly in various areas of law, from criminal to corporate law. Suppose the student decides to specialize in intellectual property law. Then what they will be doing is that they will dive deep into these different cases, the statutes, and the legal debates that are really relevant only for intellectual property. So through this specialized practice and training, they will be exposed to large amount of data specific for IPs, including adopting and navigating complex IP issues, IP cases, lawsuits, and then they will be able to offer more precise legal advice and then develop effective litigation strategies that will be tailored to this specific niche of IP. So, for example, while a general legal model, in this case a pre-trained model, is like this student that has learned all sorts of laws from criminal to corporate but hasn't yet specialized, then this general legal practitioner, in our case general legal model, will provide basic legal advice when asked about patent law, whereas the fine-tuned model, the specialized student that has seen a lot of IP-related data, will be able to provide and deliver detailed guidance on patent filing process, infringement analysis, specific case law references, etc. So to be even more specific, if we look at these two different chatbots, one is based on the pre-trained model that has seen general data, like our general student that has seen a lot of different sorts of laws. And then the other one is a fine-tuned model, a chatbot that is based on this fine-tuned model and has seen specialized IP-related data. The base model, when we are asking, can I patent my new software algorithm, would then answer, if your software is unique, you might be able to patent it. It's best to consult with a patent lawyer. Now we have the fine-tuned model, and then the answer to exactly the same question is, to patent a software algorithm, it must offer novel technological solution to a technological problem. Detail the specific ways in which your algorithm improves performance or efficiency. You should file a utility patent application, including claims that highlight the technical benefits and innovative steps. Let's prepare detailed documentation to support your claim. You can see how different the answers from this base model versus fine-tuned model are also in this case. So these examples, this one and also the previous one, it show how fine-tuning enhances this model's responses, making them more precise and practical for specialized tasks. The medical example showed the model giving a specific diagnostic advice that is really important for potential cancer symptoms instead of just asking a person to keep an eye on it, which is not super professional either. And then in case of the legal professional specialized in IP law, you can see that the base model was just saying, well, it needs to be unique, something that you might have already know when asking that question, versus the fine-tuned model that provides you specific directions and is able to better answer your questions related to the complexities of the intellectual property. Hi there, and welcome back. So now we're going to compare the pre-training to the fine-tuning when it comes to large language models. So language models like GPT-3, GPT-4, Llama, Llama 3, Falcon, all of them, they are incredibly powerful tools that can understand and generate human-like text. These models are initially created through the process that we are referring as pre-training. Now, this is a really important step when it comes to language models, and it's mandatory. Unlike the pre-training, the fine-tuning is not mandatory, but it is actually essential when it comes to building a proper language model. So it's like going to the high school and going to the university. Going to the university is not mandatory, but it's actually recommendable, or at least if you don't go to university, that you instead do it homeschooling or you specialize in somewhere such that you can earn well, you can build a career. So even if you don't go to university, you still need to read some sort of books, you need to choose a career for you, you need to whether become better in finance or in economics or hairdresser, then you need to practice more on these different haircuts, etc. You get the idea. So there is part about learning everything in one place and becoming a generalist. Usually this comes with high school, with basic school, and then after that you need to learn something new, something specific to perform a specific task in a proper way. And that's what we do as part of the fine-tuning. Now, as part of pre-training, in more technical terms, the pre-training involves training a language model on a massive amount of text data. And examples of pre-trained large language models are the GPT-4, the BERT from Google, Roberta from Google, and then GPT-4o, the recent version of GPT-4 series from OpenAI, Llama 3, also recently released by Meta AI. This list is just a very small portion of them. So think about the Falcon, the PyTorch, and all those language models that are originally pre-trained. So when it comes to pre-training a large language model, the pre-training involves training this language model on a massive amount of text data. And the criteria of those data sets that we are using for pre-training them is that they should be A, very large, B, very varied and versatile, so they are from different sorts of topic areas, from biology to literature, English literature, and then different specific data, but not too specific. So genetics, biology, textbook data, news data, even like conversational data that is stored somewhere across websites. So to be more specific, an example of such data set that you can look into to get an understanding, high-level understanding what kind of data is provided to the modern LLMs, including the GPT series or Llama, is to look at the data that is called the pile. So this piled data, it is a large, varied collection of text that contains all sorts of data. So this is an example of a data set that is very large. It's like over 800 gigabytes of data. And this type of data sets, it usually contains ton of book data, so ton of books collected in one place, not just the scientific books or school books, but also the books like fiction, etc., so literature, and then all sorts of scientific journals, research papers that have been published across many years, and a lot of tons of scraped data, so from different websites, not just Wikipedia, but ton of different websites. So this is just a very small portion of the data set that they are using. They combine this with a ton of conversational data, the language that on the street people would use, dialects, and this ensures that they are using a large amount of, so the quantity is there, a large amount of data, but also they are trying to make sure that the quality is there. So they are not trying to provide a garbage data as an input for an LLM. And as we learned as part of the previous section when we were discussing this in detail, this pre-training process, including the data pipeline for LLMs, that the quality is really important for this data. Usually during the pre-training stage, the data is being cleaned, all the outliers are removed, the extra text, unimportant text is removed, and ensure that data is of high quality and the quantity is there. Because otherwise, if you provide garbage in, you will get a garbage out. So that's a really important part for the model to learn to predict the next word in a sentence. Now, this is also another aspect for the language models. So this is the example of the piled data. As of the moment that we are recording this video, unfortunately, this dataset has just been made unavailable, but you can check it out now whether it is available. And as an example of a dataset that is being used by the companies like OpenAI, etc., this dataset contains over 825 gigabytes of diverse open source language modeling data that is consisting of 22 smaller high-quality data sets combined together. So it's really important that they mention here high quality. And this comes back to the idea that if you do not provide high-quality data to the pre-training model, then you won't be able to create a language model that is able to perform general tasks. All right, so that's about the data. Then let's quickly refresh our memory on the pre-training process that we have learned also as part of previous module in detail. So during the pre-training, a large language model, let's say the one based on transformer architecture, and this one comes from the Attention is All You Need paper, then the model takes in the input embeddings, which are these secret codes that describe the semantic representation of the words and then subwords. And this is really important and of the essence for the model to learn the semantic representation of the words and the text. Then we are adding the positional encoding such that the model will know where the words are coming from. Then we are adding the two to each other to create the final input, and then this final input will be decomposed into queries, keys, and value matrices. Here you can also see the weights matrices corresponding to each of those matrices, which are really important. And then we are decomposing this sets of queries, keys, and values as part of our multi-head self-attention mechanism into multiple heads, such that the submodels will see different sides of the words, so different features of the words every time in each of these heads, and will learn the context behind the words from different perspectives, so different characteristics of these words. And in this way, we will be able to learn the context behind the words better. So this is the idea behind multi-head self-attention in a very high level. So if you want to learn more about this transformer architecture, the pre-training process, the multi-head attention, and these different parts, please make sure to check the previous module as part of this course, because in here we are just refreshing the memory very quickly to compare this back to the fine-tuning process. When it comes to the pre-training process, the idea behind the pre-training process is to follow this structured approach, which we also did as part of our end-to-end case study, where we pre-trained our own large language model and we called it a baby GPT. So make sure to check that one out too. And here what we are doing is that we are simply following this architecture of a large language model. Assuming that our large language model is based on this transformer architecture, then what we are basically doing is that we are generating the input embeddings from our large text, we are adding the positional encodings, we are feeding this into the multi-head attention mechanism, and then we are adding residual connections, performing layer normalization to stabilize the network, putting this into the forward network, so fully connected feed-forward network, adding residual connections, layer normalization, doing this in the blocks to add more complexity to our neural network, then taking the keys and then values, providing this as an input to the multi-head attention in our decoder, combined with the queries from our decoder, and then here we have this next part where you can see the output embeddings, the positional encoding similar to the encoder part, and then here with the difference that we have masked multi-head attention in the decoder part to ensure that the model is not picking into the future words when predicting this next word. And then we are doing a similar thing like I just mentioned, taking the keys and the values from the encoder, combining with the queries from this masked multi-head attention from the decoder part, and then fitting it into the multi-head attention, then adding residual connections, layer normalization, feed-forward network, etc., up to the point of reaching the output of the model, the raw probabilities, the unnormalized scores. Then we are performing this step of computing the logits and then performing the softmax transformation. This is in the natural the architectural transformer model, and most of the modern LLMs in the pre-training stage, they look like to this transformer model in one way or the other, or maybe adjusting it a bit, decoder only or encoder only, or both of them are specialized. And then the essence of this is basically going back to the fundamentals of deep learning, which is performing these forward passes, computing the output, so predicting the next word, and then comparing it to the actual word, so the actual value of y, and then computing the loss that we are obtaining, taking the loss, performing our backpropagation, computing our gradients, so first order derivative of the loss function with respect to our model parameters, so the weights and bias parameters, taking this and providing us an input to our optimization algorithm, HGD, GD, or the Adam W RMS prop, doesn't matter, so you can pick it for yourself, and then taking these gradients, using them to update the model parameters and performing our backward pass. And the cycle goes on and on until our transformer model reaches to the maximum number of epochs or any other stopping criteria, and we end up with a bunch of values for our weight parameters and our bias parameters, which form the final model. So when we are saying that the model is pre-trained, we mean that we finish the training of transformer model at some point, and we end up with a file that contains these different values for our weights and for our bias parameters. And given that we are dealing with large language models, this is usually a file that contains billions of those values, so billions of parameters, which we are also referring as internal parameters for our large language models. So that's basically the idea behind pre-training process, and the goal in the pre-training model is to generate these probabilities for the next word. And an example of this is, for example, if we have the cat set on the, and then we want to predict the next word, then the model will generate probabilities for each of the words that are candidate words in our corpus, and many of them will have a zero probability. So when the next word cannot be, for example, a cafe or a restaurant, etc. But when the word is, for example, met, then there is a 70% chance that that's the next word. The word table has a 50% chance to be the next word, and then the floor, the 10% probability, the chair, 5% probability, and the sum should be 100%. So based on this, then the model decides that the next word would most likely be the word met, such that the sentence becomes the cat sat on the mat. So this is the idea behind the pre-training process. If you want to learn more about the fundamentals of language models, this idea of generating the next word, please make sure to check the previous modules as we are discussing this in detail, but this is just for a quick refreshment of the pre-training process. When it comes to the resources, the pre-training is highly resource intensive. So pre-training requires significant computational resources, often using powerful GPUs. So this way, we can then create models like GPT-4 that are very powerful. But this also means that you cannot just do that at home. It's not feasible to train such large language models at home because it requires a specialized hardware, it requires a significant amount of computational power. So pre-training is one of the most resource-intensive parts of the entire LLM lifecycle. That's why you can hear that people like Sam Altman, CEO of OpenAI, or many other CEOs from these big tech companies that are running the AI race, that they will continuously talk about NVIDIA, the different chips and processors, GPUs, and then millions, if not billions of investments when training their large language models. Because the pre-training requires significant computational resources, often using these powerful GPUs. This is why creating models like GPT-4 is just not feasible at home. It requires specialized hardware too, and a considerable time to invest when training such models. Alright, so now when we're clear on the pre-training, we have refreshed our memory, we are ready to move on to the fine-tuning stage. If any of those parts seem unclear, the architecture of the model, the self-attention mechanism, multi-head attention, these different matrices, or predicting the next word idea, please make sure to check the previous modules and the previous part of this bootcamp, because we here have just refreshed our memory on the pre-training stage. To truly understand the fine-tuning, you also need to understand in the proper way the pre-training process. And the previous modules as part of this course will help you to do so. Alright, so let's now talk about fine-tuning, the specializing of the large language model. So after pre-training, the model can perform general language tasks, but it might not excel in specific domains. And this is where the fine-tuning comes in. Fine-tuning involves taking this pre-trained model and further train it on a smaller, domain-specific, sometimes your own dataset, to specialize it for a particular tasks. So examples of such a process is ChatGPT. So ChatGPT is a fine-tuned version of GPT-4 model at the moment, optimized for generating conversational responses. Now this is really important. The pre-trained model GPT-4 is, for example, not optimized for generating conversational responses. Unlike the ChatGPT, which is the fine-tuned version of the GPT-4, at the moment also GPT 4.0, that is able to generate conversational responses at a high quality. For example, if we compare the base pre-trained model, the one from GPT-3, with retail customer support expert, that is the fine-tuned version of the GPT-3, so someone took a lot of customer support data and use that to fine-tune this GPT-3 model, then here are the responses that the two models will provide. The GPT-3 will take the question, the prompt will be, I haven't received my order yet, can you help? And then the answer from the plain pre-trained GPT-3 model would be, sure, I can help you with that. Please. So here is an example of a pre-trained GPT-3 model from OpenAI versus the fine-tuned version, so taking the pre-trained GPT-3 model and then specializing it in a customer support and making a retail customer support chatbot. So this is the fine-tuned model that is based on a ton of customer support related data. So you can see in the left-hand side that the prompt is, I haven't received my order yet, can you help? And we are providing the same prompt to the fine-tuned model, the customer support chatbot. So the base GPT-3 model will then provide us the answer, sure, I can help with that. Please provide your order number and I will look into it. While the fine-tuned model will say, I apologize for the delay in your order. To check its status, please provide your order number and email address. You can also track your package using the link in your shopping confirmation email. If you need further assistance, please let me know. So you can see what a difference it makes when we have the retail customer support expert, the chatbot fine-tuned model, providing the answer versus the plain GPT-3 model. You can see the detail, the quality of the answer, and how, from the customer point of view, it would be satisfactory to see the completion, so the answer that comes from the retail customer support expert versus the plain GPT-3 model. And that's the power of fine-tuning a large language model. So let's now quickly talk about some technical details before getting into the specific comparison between the fine-tuning and the pre-training. So when it comes to the fine-tuning and the technical details behind it, it's really important to understand the difference between the weights and the bias idea when looking into the fine-tuning process and pre-training process. So let us quickly talk about the technical details behind the fine-tuning before diving deeper into it. So during the pre-training, we are generating these different weights and we end up with this optimal weight parameters, billions of those parameters for the internal model. When it comes to the fine-tuning, similar to the pre-training, the fine-tuning involves updating this model weights and bias parameters, but with a focus on a specific task. So we're using a smaller data set that is specialized data using this idea that it should be specific, it should be smaller, and this data set is relevant for our specific task or domain. If we want in a legal area the specialization, then we need to provide more legal data and more specific data. If we want the model to be specialized in a IP law, so intellectual property law, then we need to provide more of this type of data. Or if we want the model to answer a customer support related questions, then we need to provide this type of question answers set to the model. We will dive into the specifics in detail later on. But for now, let's keep the focus on the technical side. So when it comes to the weight updates, the pre-trained weights serve as the starting point. So during the fine-tuning, these weights that we got from the pre-training process are then adjusted one more time. So they're further adjusted to minimize the errors on the new task-specific data. So during the fine-tuning, we are taking the weight and bias parameters and all these billions of parameters from the pre-training stage, the final model that we got from the pre-trained stage, and then we need to continue the update of these weights. In the fine-tuning, we are updating the model weights and biases, but with a focus on a specific task. So if we have a specific data, so we are changing the data, the optimization process changes. So every time we need to predict the next word or we need the model to perform a specific task. That means that the error associated to these weights will also be different. And now this time the goal is to ensure that the model continuously updates this weights that was provided from pre-trained model such that it will minimize the errors on a new task-specific data. So the data will be smaller, more specialized, but this process still stays the same, continuously updating and adjusting the weight parameters to minimize the loss that the model has on this new task-specific data. So this is the process of further tuning of these parameters, hence the name fine-tuning. And this fine-tuned model will then result in a set of weights and bias parameters that results in a smaller error, smaller loss for this specific new data that we have provided to it. A couple of things to keep in mind is that we are calculating this loss, so calculating the error that the model has on this task-specific data, which indicates how well the model is performing on this new data. Then using the techniques like gradient descent, AdamV, RMS probe, we want to minimize this loss, further refining the model's weights and biases. There are a couple of things that we will discuss in detail once we go through the process step by step, which involves the amount of change that we need to apply to our weights, because the idea is that we don't want to change the weights a lot, as the pre-trained model provides us a lot of important information that we don't want to lose. And at the same time, we also want to change them at some degree. And this can be controlled by the learning rate from the optimization algorithm. But we will talk about these details when we will discuss the technical stages of conducting a fine-tuning step by step. For now, just keep in mind that we are changing the weights that we take as starting point from the pre-training process, and we will change them until we minimize the loss of the model for that specific data that we use for the fine-tuning. Now, this is in the nutshell the difference between fine-tuning and pre-training. So we will dive into these different parts, how you can fine-tune it, what are the technical details behind them, once we approach the fine-tuning step-by-step process. But for now, those are at high level the differences between fine-tuning and the pre-training. Let's now compare the prompt engineering to the fine-tuning. Let's compare fine-tuning with prompt engineering. So, prompt engineering involves creating specific inputs to get the best responses from the model without changing its core structure. When it comes to prompt engineering, this is something that I'm 100% sure that all of you have already experienced in one way or the other. If you have used ChatGPT, then you have definitely done prompt engineering. You have provided the prompts to the ChatGPT and then it created back an answer for you. While the fine-tuning, on the other hand, it most likely, if you are in this course, that you haven't yet done the fine-tuning. Fine-tuning is the changing of the model itself, making it more specialized and improve it so that it can understand and respond better based on its specialized training. So prompt engineering involves crafting the specific prompts or instructions or inputs to elicit these desired responses from a pre-trained models without additional training. You just go to the application, you provide the prompt, and then you are getting a feedback. It leverages the model's existing knowledge base and capabilities. You are not adding any extra data, no specialization, no extra tuning, extra resources, just plain improving your quality of the questions. While the fine-tuning is not like that. It does involve resources, some knowledge that you need to apply in order to perform the fine-tuning. You know, when you go to Google or YouTube and type something into the search box, you're trying to get exactly the information or the video that you are looking for. You want to phrase your question in a certain way, such that you can get the best answers, right? So that's essentially the prompt engineering. It's all about how you ask a question to get the best answers out of the system, like a search engine or a chatbot, or in our case, an AI application. So whether you are typing something into Google, asking Siri a question, or even deciding what to type into a chatbot on a website, you are engineering the prompt, hence the name prompt engineering. A great example is when you interact with ChatGPT. So you might have noticed that the way you phrase your question or prompts, this can significantly influence the type of responses you will get. So many people are even saying that if you use the GPT-4 but combine this with bad prompt engineering practices, so you just provide poor prompts, then you might get worse response than if you were to use GPT-2 but with a high quality prompts. So it's really important what kind of questions you're asking and how you formulate it. In here you can see that when I'm asking what is the weather like in Amsterdam, that the quality of the answer is really different. Let us actually hear two examples. So you can see that when I'm asking what is the weather like, then the answer is, could you let me know which specific location you are asking about for the weather update? While when I'm specifying the location as well and also the date, so I'm saying what is the weather like in Amsterdam today, you can see that I'm getting a direct answer. I'm getting that today in Amsterdam the weather is characterized by scattered showers with passing clouds. The current temperature is around 64 Fahrenheit with a high expectation to reach about 73 Fahrenheit. It provides me humidity level, it provides me information about the wind, in which direction it's blowing, the speed of it, and what I can expect from the evening, which will be mild and cloudy atmosphere. So you can see that dependent on the question quality, the prompt quality, the answer from the AI application will be different. So the same in here. You can see when I'm saying translate this sentence into French, hello, how are you today? Then the French translation for hello, how are you today is bonjour, etc., etc. But when I'm saying translate the sentence into formal French, and then I'm saying the sentence, then you can see that the answer is slightly different. Because in the first one, although my intention might have been to get the sentence in a formal French, but the prompt that I formulated, it didn't convey the motivation that I had. So you need to specify those details. You need to also provide examples, like in here when I'm saying try to translate this dialogue into formal French suitable for business setting. So I'm specifying the setting, what kind of language should it be used, and also providing an example, like if the person A says this, then the person B is expected to say that. So in this way, I'm teaching the model without doing training, etc., without spending resources, just by using the quality of my prompts and improving the quality, reaching better results. And that's the idea behind prompt engineering. So in this way, by shaping the questions to guide the AI towards the kind of answers I want, I can get high quality answers without spending resources and without requiring knowledge. So it's simple, it's something you are already familiar with, I'm sure you have used it, and it doesn't need any special data, specific data, or tech skills. It's about being clever with words and instructing the model to do exactly what you want it to do by providing examples, by providing all the details, spelling out all the minor characteristics that you want the answer to satisfy. It's a simple adjustment in how you formulate your questions and how you ask something, but makes a big difference in what you will get from the model. So let us now quickly lay down all the pros and cons of prompt engineering versus fine-tuning. So let's start with the pros of the prompt engineering. So when it comes to the first benefit of prompt engineering is that it doesn't require data. So you get to work with what the AI already knows, so what the underlying model already knows. So there is no scramble for new data. You don't need data engineering skills, data science skills. It's super handy, especially when gathering fresh data is tough or privacy issues are concerned, even if you have the knowledge to gather that data. So the next benefit is the lower cost. It's pretty cost effective as you are not spending on retraining, fine-tuning the AI model. Just use what's already there. You just need to tweak the inputs a bit, formulate it a bit, add some more text and examples, so be a bit more creative with your words to fine-tune the outputs without breaking the bank and without actual fine-tuning process. Next up is the accessibility. This one is a huge advantage for prompt engineering side because anyone can do it. You don't need to be a techie, tech-savvy person, a data scientist, a researcher, or a programmer. If you can ask just clever questions, you can use the chatbot effectively and go a long way. Another advantage is the accessibility. So anyone can do it. You don't need to be a tech-savvy person or a scientist, a researcher specialized in AI in order to improve the quality of your questions. So if you can just ask clever questions, you can just use that model effectively. Next advantage is the dynamic data integration. By using smart techniques like the retrieval augmented generation, so the RAGs, the model can pull into the latest info on the fly, keeping the conversation fresh and relevant. So if you can combine this idea of base model with a RAG or RAG-based model, then this would be ideal because sometimes we want our answers to not just be relevant, but also be up to date, because it can be that the answer is still correct, the answer that is provided by the model, but it's based on the time and relevant for the time being when the model was pre-trained, but not up to date. Because if the model was pre-trained, for example, last year, and you are using it now, then the answers will be correct for the previous year. But it can be that there was a change in the answer, and you want to get the most up-to-date information. And that's where the systems like RAG are very useful. And we will be dedicating an entire section for this part and for this technique to dive deep into the RAGs and then to practice it. But for now, just keep in mind that this is a huge benefit from prompt engineering. By trying to ask the questions in a clever way, you can get the most up-to-date information if the underlying model is supported by RAG, keeping the conversation fresh and relevant. So next up, let's talk about another advantage of prompt engineering, which is the speed and efficiency. So if you need a quick answer, the prompt engineering doesn't make you to wait for it like we do it with fine-tuning. So it's like asking a friend a quick question, and if you formulate in a good way, then you can get an instant response, which is perfect for real-time customer service or lively chatbots. So if you want to every time specialize your model, then you need to perform fine-tuning. but this is just not possible if you want to get the answer instantly, if you want to get the results instantly, because fine-tuning takes time. You need to gather your data, you need to understand what you need to do, you need to pick the technology, obtain the resources, then perform fine-tuning, put the data into its place, whether it's batching or streamlining, then finally get an answer. So after productionalizing the model. So an entire headache that can be avoided if you can ask the questions in a clever way, and that's still a possibility. So you don't need to implement the fine-tuning right off the bat. Now let's talk about the cons of prompt engineering that might motivate you to go on to the bit more difficult friend of it, which is the fine-tuning. So the first limitation of prompt engineering is the limitation by data fit. So what do I mean by that? So you are stuck with what the model already knows. If it hasn't learned, for example, the latest TikTok trends, then it might not keep up with the conversation about the viral content. So if you go ahead and ask what are the latest trending hashtags on X, then unless the model was trained very recently, then it will just provide you old trending hashtags. And that's something that you don't want. So for those cases, then the prompt engineering might not be very handy. So next up, we have the memory limitation. So there are only so much that the model can handle at once. Asking for too much information in one go might overwhelm the model, and it will limit how deep your answers will get. There is also a high risk of hallucination. So if you formulate your prompts wrongly or inaccurately, then the model might start making stuff up. It's like playing a game of telephone. The end result can sometimes be way off than the initial input because it goes through all these different stages, and then combine it with the wrong prompts, then you are getting the wrong response. Next up, we have the dependence on the model quality. So everything hangs on how good the underlying AI model is when it comes to prompt engineering. The dependence on the model quality is a big disadvantage when it comes to the prompt engineering. So if the quality of the underlying model is bad, then the output that you will get will be also bad quality. So a poorly pre-trained and fine-tuned AI model won't do the wonders that you can expect. So no matter how clever your prompts will get, if the underlying model is bad, then you won't be able to get good answers. The idea is that prompt engineering will be improving the quality of the responses that you will get as you formulate right questions, assuming that the underlying model is a good one. But if the underlying model is a bad one, then independent how much you will improve the quality of your prompts, the answers that you will get won't be of high quality. So let's now discuss the benefits and the demerits of fine-tuned models and why we need to do fine-tuning in the first place. So first up, we have the specialized knowledge. So fine-tuning allows the AI to become highly proficient in a specific area, such as interpreting legal text or diagnosing medical images, specializing in customer question answerings, etc. So customized knowledge is the number one benefit of fine-tuning a model. Next up, we have the reduction in errors. So fine-tuning significantly reduces the amount of errors that the model will make. It enhances the reliability of the model for critical tasks that require high accuracy. So you can expect that the fine-tuned model, at least if the fine-tuning has been done properly, that those models will provide much more accurate responses than the other models would do. So next up, we have the enhanced adaptability. So a fine-tuned large language model, it acts as this expert in its domain in the specific task that it has been fine-tuned to do. So it provides more accurate responses without the need for the constant adjustments. So you don't need to apply too many of these prompt engineering steps and too much info to the model to provide you a good responses. So next up, we have the long-term cost efficiency. So while there are initial investments with fine-tuning makes the AI much more efficient, reduces the computational resources that is needed over time, and saves the money in the long run. So the initial investment might seem large, but in the long term, you will see that it just pays off. So let's now talk about the demerits of fine-tuning. So what are the cons of fine-tuning? So first up, we have the resource-intensive nature of it. So fine-tuning requires substantial computational power and extensive data sets, which can be costly and difficult to obtain. Because it costs you money to hire a data engineer to collect data and prepare for it, or a data scientist to do that job. In this highly competitive market, when professions like this cost a lot of money, also, it requires a lot of GPUs to fine-tune a model, not as much as the pre-training, but still some money to do fine-tuning, unlike the prompt engineering that doesn't require any of those. It also requires knowledge, which sometimes costs a lot of money, and requires other sources of investment, including the investing in the programming languages and many licenses or libraries that you need to use or environments you need to use, etc. So this all can be costly and very difficult to obtain. And then next up, we have the high upfront costs. So kind of related back to the idea of resource intensity. So the initial setup, including the data collection, the web scraping, model tuning, it involves significant financial investment that not everyone has, unfortunately. So next up, we have the need for technical expertise. Fine-tuning, it requires advanced technical skills for the setup and for the optimization of large language model that often requires specialized people like specialized data scientists, AI engineers, machine learning engineers, data engineers, such that they can, in a proper way, fine-tune the model. Finding this type of experts is really difficult. Not just that it costs a lot of money to find them and pay them, but also very difficult to obtain them. Fine-tuning requires a lot of knowledge, like the idea of these different strategies you can use, choose the right fine-tuning topic and fine-tuning model to apply the fine-tuning process in the proper way, starting from the data collection, cleaning the data, putting it into the right format up to the point of fine-tuning and then productionalizing the fine-tuning model. It all is based on a large amount of technical expertise, and finding them, it is costly but also very difficult. Next up, we have the scalability challenges. So fine-tuned AI models, they excel within their specific niche, but may struggle when applied to new areas, often requiring this retraining of the model and repeating everything once again for this new specific task or new type of domain of expertise, which adds time and then costs, of course. So unless you are a startup that is funded or you have your own personal funds for fine-tuning every time for these different sorts of tasks, it will be quite challenging for you to afford these different fine-tuning processes for different tasks. So choosing between prompt engineering and fine-tuning depends really on your specific AI needs, but also resources that you got. If you have funding and you know that prompt engineering won't solve your problems and you really need to specialize in specific area of expertise and you want your model to perform specific tasks, then the fine-tuning will be your choice. And when it comes to the underlying model being already good enough and you don't have the resources, so you need to work on your prompts quality, then prompt engineering will be your friend. Depending on your specific case and your resources, you can choose which one would be more appropriate for you. Alright, so we are done with comparing the prompt engineering and fine-tuning. We are ready to move on to the next topic, which is the actual fine-tuning process, and to start to get a bit more involved into the technical details behind fine-tuning a large language model. So bye for now, and I will see you in the next session. Hi there, and welcome back to another session about fine-tuning a large language model. In this session, we are going to talk about the step-by-step process behind fine-tuning LLM. Fine-tuning is a powerful technique to transform a general-purpose language model, LLM, into a specialized tool. Much like the doctors who specialize in oncology or dermatology after learning the fundamentals in medicine. It leverages the knowledge gained during the pre-training step on a massive text corpora and adapts it to specific tasks. So let's now dive deeper into each of those steps that form this entire process of fine-tuning a large language model. First up, we have the objective. So we need to clearly define our objective for fine-tuning. So clarity is really the key here. Be extremely specific about your goals. For example, do you want your LLM to accurately classify customer reviews as positive or negative, so to perform sentiment analysis? Or you want it to generate creative marketing copy in a particular brand voice? Or you want it to answer complex questions about medical diagnosis, like domain-specific knowledge? Another one is measurable goals. So you need to set the goals measurable. So establish a metrics to guide the success for your fine-tuning process. Examples include accuracy in sentiment analysis tasks, or human evaluation scores for generated text, or performance on relevant benchmark datasets. So we are going to dive deeper into these different tasks that you can perform, this downstream task, as well as the metrics that you can use depending on the task that you want to achieve with your fine-tuning at the later stage in a separate section as part of evaluation of large language model. But for now, keep in mind that independent what kind of task you want to do, for that task you need to get the clear objective and you need to find metrics to measure the performance of the model. So have you achieved your goal with fine-tuning of your model or not? For that, you need a specific, measurable goal and metrics to guide that process. So next up, we have the gathering and preparing the data. So first up is the quality over quantity. Focus on acquiring high-quality data that mirrors the real-world scenarios your model will encounter. Especially when it comes to fine-tuning, the quality of the data is of utter importance. If during this pre-training, given that you have a ton of data, some bad quality data might just squeeze in and not affect the performance of the overall model, during the fine-tuning, even the small portion of low quality data might affect the performance of the model. So be very careful with the quality of the data, ensure that it's collected properly, it is reliable, it doesn't contain outliers, etc. So pretty much following the process of the data pipeline for LLMs that we have learned as part of previous module. So clean the data. Data cleaning is really important. Remove the errors, remove the inconsistencies, the irrelevant information, any outliers that you have identified as part of the quality check from the previous step. For instance, if the fine-tuning for the sentiment analysis needs to be done, then correct the misspellings or grammatical errors, filter out the neutral reviews that do not contribute to the learning, and leave the positive reviews and the negative reviews. It's really important to remove the errors, inconsistencies, outliers, and irrelevant information. So if in the previous step you have performed your quality check, this step should be quite straightforward. And then dependent on the task, for example, if you are doing fine-tuning for sentiment analysis, meaning that you want to, for example, classify a text being positive or negative review, then you need to correct the misspellings, you need to remove the grammatical errors, you need to filter out the neutral reviews that do not contribute to the learning. So if needed, you also need to do annotation. So for certain tasks like in sentiment analysis, you might need to label or annotate your data. For example, in the case of figuring out whether the review is positive or negative, so in sentiment analysis, we might need to label each review as positive and negative or neutral if needed, such that we can guide the model what is correct and what is not. Such that once we do the fine-tuning, the model understands this review should be considered as positive. Meaning, if you have specific text, so for example, a review that says, I absolutely love this product, it exceeded my expectation, then the annotator should put there a positive. If the product is okay, nothing special, so the review is that, then the label should be neutral. Otherwise, if it says, I'm very disappointed with this product, it broke after one, usage, then the label should be negative. And if you're wondering who should do this annotation, well, this depends. Some people have a highly accurate models that can perform this labeling for them in the first place, like a classification models. And some people, when they have resources, then they can ask the humans to do the annotation, unless the data is so large that they don't have that option is not visible. So next up, you need to choose the pre-trained model. consider your specific needs. What kind of problem you are trying to solve, what kind of applications you are trying to build. For general language tasks, models like GPT-3, GPT-4, GPT 4.0, Llama 3, BERT, they are all excellent choices. Of course, this really depends on what kind of problem you are trying to solve. So, specific to your problem, you might go for decoder-only architectures or encoder-only architectures or encoder-decoder architectures. And then depending on that, you will then go with different pre-trained LLMs. And when it comes to the specialized domains, so let's say you are trying to build a medical chatbot or a legal chatbot, then you might want to explore models that are pre-trained on that specific relevant data. Because the model, pre-trained model that is pre-trained on relevant data, let's say legal data, then this will definitely result in much better fine-tuned legal model and legal chatbot than the general GPT-3 or BERT. So next, you also need to decide on the architecture, and that is what I was just referring when I said the decoder only, encoder only, or decoder encoder, or specialized. So most large language models, they are based on the transformer model. So that's something that we have seen before. We learned about this architectures, the different sorts, but also we saw this transformer architecture consisting of these different layers, starting from the self-attention, so multi-head self-attention, then adding the residual connections, the layer normalizations, the feed-forward network, and then providing these keys and then values onto the multi-head attention from the decoder part, where it is combined with the queries coming from the masked multi-head attention, and so on. These layers enable the model to capture the complex patterns and the relationships within text data. So it's really important to go for the LLM that you know that is most likely is of high quality, and that is usually the transformer-based LLMs. So also the size matters. Large language models often have greater capacity but require more computational resources. So try to balance your requirements with available resources. A fast repository of pre-trained models is the Hugging Face. So if you are looking for an open source model, try to check the Hugging Face, because there they have so many options in their intuitive UX. There you can choose for Meta's LLMs, you can choose for the 8 billion version or the 80 billion option, and then you can choose for the Llama LLM. You can also go for the OpenAI open source large models. So the sky is the limit here. There are so many options that you can choose from. As long as you know how you can choose the right language model, that would be a great way to start your fine-tuning process. If you are looking for a guide on how to choose the right large language model, then make sure to check the section where we are talking about choosing the right LLM. We have an entire session dedicated to this. So in here you can see that I'm looking at the documentation provided by Meta specifically for Llama 3 that has been recently released. So on April 18, 2024 to be more specific. So a couple of months back, and you can see that they are providing a whole bunch of information, including the code that you can use to implement it in PyTorch, and a lot of supporting documentation, how you can update the weights, the BAS parameters, and how you can implement the model. Next up, we have the actual fine-tuning setup. So, depending on the task that you want to perform using this fine-tuning, you might add task-specific layers to the pre-trained large language model. For example, in the text classification, you might want to add a linear layer on the top of the transformer layers to produce these class probabilities, such that once you generate these logits and then perform your softmax transformation, you can generate probabilities that say for this class the probability is that, for this class the probability is that, and then based on that you can then select the answer with the highest probability in terms of the classification. So depending on the specific task, you might need to add extra layers to pre-train the model to adapt it to the network's needs. So depending on the specific task, you might need to add extra layers, this neural network, fully connected neural network layers, to the pre-trained model to adapt it to your needs. For example, for text classification task, you might want to add a linear layer on the top of the transformer layers to produce these class probabilities. Like in here, you can see that we are trying to add this dense layer. And for example, if we want to perform sentiment analysis, then this would be highly appropriate. We might need to add this dense layer on the top of our base transformer model to create this neural architecture for our specific case. And then when it comes to the calculation of loss function, so to measure how good our model is for our specific sentiment analysis or classification or any other task, we need to measure this using a matrix. And the loss function will then measure this discrepancy between the model's predictions and the ground truth labels, so the labels that we know they are true, and then we can calculate this. We can calculate this loss. And the common loss functions for fine-tuning include cross-entropy loss for classification, or mean squared error for regression tasks, or the mean absolute error, the root mean squared error, and many others. So the loss function is really important. We will talk about this one when discussing the evaluation of large language models. But for now, what is relevant is to keep in mind that when it comes to the fine-tuning process, like in case of the pre-training, we still need to perform this evaluation, understand how well the model is doing. But this time we want to know specific for our case. If it is classification, then we need to use classification matrix in order to understand how well the model is performing the classification task. So when it comes to the computational power, you need to ensure you have access to sufficient computational resources, so GPUs or TPUs for efficient training. Now this one is really important. Ensure that you have access to powerful computational resources, so graphic processing units or the tensor processing units, which is really important for efficient fine-tuning, especially when dealing with large models like the ones coming from Meta, the ones coming from OpenAI. Those models, even though there are different sizes available there, so 8 billion or 8 billion or others, even for the smallest one, you need quite some computational power, at least some GPUs. So examples of GPUs are the NVIDIA's RTX 3090 or the one of the A100 that is also highly popular across the industry for the commercial use. And those GPUs or the TPUs coming from Google Tensor Processing Units or the TPUs, the Google Tensor Processing Units available on the Google's cloud, those will be essential for you to fine-tune your large language model. So experiment with different values for your learning rate, like when you are performing your optimization process, like in case of pre-training. So next up, you need to perform hyperparameter optimization. Experiment with different values for your learning rate, so how quickly the model is learning. The batch size is another parameter that you need to keep in mind, so the number of samples processed at once. So next up, we have the training process. This is a really important part when it comes to fine-tuning process, and it is the improvement of the model weights and bias parameters, the internal parameters of our large language model, such that we can optimize it for our specific use case, for our new data. So imagine you have your pre-trained model, you have selected it, you have set up everything in place, and now you have this final weights and bias parameters and this new data. So you will then start with these parameters that you have as your starting point from pre-trained model. You will then train your model with these parameters on your new data, and what the model will then need to do is to gradually adjust these weights and the bias parameters to minimize the loss function. So use algorithm like stochastic gradient descent or ADAM or ADAM-W, so an optimization algorithm, in order to update the model weights and the bias parameters using this optimization algorithm to minimize the loss function for this specific new data. We are pretty much repeating the same process as with any other neural networks. Forward pass, backpropagation, computing the gradients, using this as an input for our optimization algorithm, and then updating the weights and bias parameters. Only now, during the fine-tuning, we start from this state where we have the certain values for our weights and bias parameters, and we have a new data, small data and specific data, and we want to minimize the error that the model is making, minimize the loss function, which involves backpropagating this error through the network and adjusting the weights accordingly using this learning rate for our fine-tuning process, and then updating these weights and bias parameters again. So fine-tuning typically involves smaller learning rates and batch sizes compared to the pre-training. This one is really important, and I cannot express enough how important it is to ensure that you don't mess up with the pre-trained model and that you lose all the important information that is in those weights and bias parameters. Because after all, it's not for nothing that we are using a pre-trained model. So pre-trained model, if they have been pre-trained properly, like the GPT-3, GPT-4, or Llama 3, they have been trained on massive data, a large amount of versatile high-quality data using a lot of computational power and knowledge, things that you most likely won't be able to replicate at home. And there is also no need for that. You have the pre-trained model that is able to perform these general tasks, and your goal is to not completely change those parameters and these parameter values that is provided from pre-trained model, but instead to slightly change them such that they will be tweaked for your specific use case. So you don't want to change the model parameters entirely, but instead you want to just small amount that you want to adjust such that the model is performing well on this new task, on your specific task. This helps you ensure that you are making use of the pre-trained model. So by using a smaller learning rate, you will then ensure that the information in the pre-trained model is not being lost. This is really important. And by controlling the learning rate, you can then control how much information you will keep from pre-training stage versus how much information you will add from the fine-tuning stage. So fine-tuning will then typically involve much smaller learning rate, and the batch sizes also smaller compared to the pre-training. And in this way, we are preventing the model from overfitting to the new data and then entirely forgetting what it learned during the pre-training test. Highly costly process. So fine-tuning generally requires smaller learning rates compared to the pre-training to prevent these drastic changes to the pre-trained model's parameters. So also the smaller batch size help in more nuanced updates. So just to illustrate this difference between the different hyperparameters that we need to apply when combining the pre-trained models result of these weights and bias parameters that we get and the new updated version, so fine-tuning process, because we are combining the pre-training with fine-tuning, and the idea is that we want to benefit from the pre-trained model and this powerful source of information, but yet also improve it a bit by fine-tuning it for our specific data and task. Here is the difference between the two different versions. For the pre-training learning rate, we can typically take this range, as you can see, whereas for the fine-tuning, we take this range for the learning rate much smaller value. And the idea is that this learning rate controls the amount of updates we will make to the weights. If the learning rate is small, then we are making smaller updates. So to illustrate this idea between difference of fine-tuning versus pre-training, we can look at the learning rate ranges that usually we use for pre-training process as well as fine-tuning process. So the learning rate is the parameter that controls the amount of updates we will make. So the change size that we are going to apply to our weights and our bias parameters. If the learning rate is large, so our step size is large, we are then going to make larger updates to our weights. And this is fine during the pre-training process, but this is not fine during the fine-tuning process. We want in the fine-tuning to update the weights in a small amount, such that we don't lose the highly accurate and large amount of source of information that comes from pre-training process. We spend so much resources and so much time in pre-training the model, and we don't want to update the weights drastically. Instead, we want to keep this update amount minimal. Therefore, we are also using the smaller amount of learning rate, this step size. And that's something that you can see here, illustrated by these different ranges for the learning rate for pre-training step versus the fine-tuning step. During the fine-tuning, as you can see, we are using much smaller range of this learning rate. So another thing is this batch size. During the pre-training stage, we use larger batch sizes, let's say 256, 512, to speed up the training process. But during the fine-tuning, we want the model to be more precise. We want the model to have more accurate updates. Therefore, we are making the batch size smaller, let's say 16, 32, maximum 64, such that we can make more precise updates to our model parameters. So, fine-tuning often involves multiple training runs. So we want to monitor the model's performance on our validation set that we hold it next to the training set, and we want to adjust the hyperparameters as needed. Fine-tuning involves multiple training runs when the model is iteratively updated and evaluated. So we iteratively update those weight parameters and we are continuously evaluating, well, how good is the model doing on this specific task and on this specific data. This iterative process helps to gradually improve the model's performance. So when it comes to the steps that involves in here, the trained model need to be set for a specific number of epochs. So we need to run the model on a specific number of epochs where each epoch is basically running through the entire training set. Then we want to evaluate the model, the trained model, on the validation set that we hold it apart and haven't used during the training. So we then want to adjust the hyperparameters based on the validation performance and then repeat the process up to the point that we find this set of hyperparameters, let's say learning rate or batch size, that results in the smallest amount of error during our fine-tuning process. So let's now talk about the overfitting. Now, overfitting is not just an issue for the transformers or large language models, but we are aware about this problem starting from the traditional machine learning. So we have overfitting in linear regressions, in random forests, up to the XGBoost, boosting techniques, bagging, and also in deep learning models, and now also in large language models. So this is not a new issue. So there are different ways that we can mitigate overfitting, and techniques that we are using in the traditional machine learning usually also hold for this fine-tuning process. So overfitting is the process when the model performs well on the training data but poorly on the unseen data. Like with any other traditional machine learning model or deep learning model, the large language models are not exception. So they also suffer from overfitting. So during the fine-tuning, we need to be aware about this. So overfitting, just as a refreshment, is this problem when the model performs well on the training data but poorly on an unseen data. This means that the training error rate might be very low while the validation error rate might be high. And this is a problem because we want our model to be general. We want it to perform well on a new unseen data. So just to be cautious of this overfitting, where the model performs well on the training data but not poorly on the new data, is something just to be aware of. And like with the traditional machine learning, also in the LLMs, one way of solving this problem is by early stopping and also regularization, just to prevent this problem, and continuously monitoring the training error rate versus validation error rate during this fine-tuning might be super helpful. So let's actually discuss a couple of techniques that we can use to solve this overfitting problem. And this is not a new thing. This doesn't just hold for the LLMs, but for the traditional machine learning as well. So we have this overfitting problem in linear regression, in random forest, in logistic regression, up to deep learning models like the RNNs or LSTMs, and in the same way we also have this problem in the LLMs. Therefore, first thing that we need to keep in mind is to monitor the performance of the model, to compare the training error rate to the validation error rate, and continuously check whether the validation error rate is not increasing too much compared to the training error rate, because this signals that we are dealing with overfitting. And then another thing is to solve this problem. So techniques that work with the traditional machine learning and deep learning models will also work in here. Think about early stopping, like ensuring that we stop the model whenever we notice that the validation error rate is starting to increase compared to a training error rate. And then another thing is to apply regularization techniques. So think like the L1 regularization or L2 regularization, so for weight decay, or even the dropout regularization, which is perfect for the deep learning and LLM type of models. So dropout will then randomly drop couple of neurons, certain percentage of neurons in each iteration, and in this way you will decorrelate the neural networks and will then reduce the chance of overfitting. Next up is evaluation. So once you have done all these steps from 1 till 5, you are ready to evaluate your fine-tuned model. Use a separate test set to assess the model's final performance. This set should be unseen during the training and validation. So think of dividing your entire data into training, validation, and test. Use the training for training the model. Use the validation set for validating the model and tuning your hyperparameters as we just discussed and ensuring that the model is not overfitting. And only in the very final stage when evaluating the model, in this step number 6, take your test set, this third part of the data set that you haven't used at all in the previous steps, and use that to calculate your error rate. That's the most accurate error rate you can use to assess the performance of your large language model that has been fine-tuned. So evaluate across various relevant metrics, not just one. This will help you to gain a comprehensive understanding of the model's strengths and weaknesses. And if you're wondering what kind of metrics you can use and how you can evaluate your large language model, then make sure to check the module that is dedicated for evaluating large language models, because we go into the depth of these different metrics you need to use, not just the common metrics like the classification or task specific metrics, but also many other things that you need to be aware of, like the toxicity of your large language model, the truthfulness, etc. Those are metrics that usually you won't see in the traditional machine learning because we are used to using F1 score, recall, etc. just to assess the classification model. But in case of large language model, the story is different. You need to be aware of many other metrics and check your model for those. Hi there and welcome back. Let's now talk about ways you can fine-tune a large language model. There are 3 ways of fine-tuning large language models. The first one is the supervised fine-tuning. Here we use labeled data consisting of input-output pairs, and we are letting the model to learn to produce the correct outputs when given similar inputs. Another way of fine-tuning large language model is the self-supervised learning, self-supervised fine-tuning. This method involves training the model on a large corpus of text to predict parts of the data based on other parts. It's like taking a sequence of text and having the model to predict what comes next. So the idea of generating the next part. Third way of fine-tuning a large language model is the reinforcement learning with human feedback, or in short, RLHF. This method uses a human feedback to fine-tune the model's responses. Let's first talk about supervised fine-tuning of large language models. This is a technique that helps our model to become smarter by learning from labeled data. So what is labeled data? It's simply a collection of examples where we know the correct answer. We have the input and the expected output. For instance, if we have a piece of text that we want to categorize, then the data would be existing from different texts and the corresponding correct category or correct label for it. The idea behind SFT is pretty straightforward. We want our model to learn from the given examples that we provide, so it can make accurate predictions when it encounters a new unseen data next time. Think of it like teaching a child to recognize objects. You show them a picture of an apple and tell them this is an apple. Then you show a picture of a table and you say, well, this is a table. After enough examples, the child can recognize apples on their own. The child can also recognize the umbrella as an umbrella and newer objects, newer data points. So let us actually apply the supervised fine-tuning in terms of its idea and understand this supervised fine-tuning in different sorts of tasks. First up, we have semantic analysis. So let's start with this one. This is a task where we are trying to figure out if a piece of text expresses a positive, negative, or a neutral sentiment. Imagine we have a dataset of movie reviews. Each review is labeled with the sentiment that it expresses. For example, a movie was fantastic is labeled as positive. And if we have input that I hated the plot and the acting was terrible, then of course the output should be negative. If we have it was an average film and nothing special, then the output, the label is neutral. If the input is the soundtrack was beautiful but the story was boring, then the output is mixed. So this is then our label. Then we have absolutely loved it, a must watch. So the output here is positive. So this is basically the idea behind a type of data that you should provide to your fine-tuning model such that it can fine-tune the base large language model. Now in another task, let's say you have text that you want to classify. With this SFT, the idea is that you will need to categorize this text, these documents into predefined categories. So the text classification would then have this type of data ingested into the model that we want to fine-tune. So in here you can see that the input is something like the stock market experienced a significant drop today. And then the corresponding class is its finance related topic. Then we have the football match last night was thrilling and ended in ... So then the output is sports. So we are basically classifying, we're providing the labels for each of these texts in terms of the topic that they represent or the field. Another one is a new species of bird was discovered in the Amazon rainforest. Then the output that the model should provide is science. Another example that we are providing to the model to learn from is that if the input is the latest smartphone model has several new features, then the corresponding output is technology, and so on. You get the idea. So the idea is that we need to put our data for our fine-tuning process in this format with the input and the corresponding classes, predefined classes, and then we will ask the model during the fine-tuning process to, as accurately as possible, classify the newer observations to the corresponding categories. Another example of task that we might want to perform during the fine-tuning process is question answering. So let's talk about this one, as it's a very important application of generative AI models and large language models. This task involves providing these precise answers to the questions based on a given context or knowledge base. For instance, if we have a data set of these question-answer pairs, like this one, what is the capital of France? Then the right answer for this should be Paris. What is the largest planet in our solar system? Then the answer should be Jupiter. When did the Second World War end? Then the answer should be 1945, and so on. This is the idea behind this specific data that we need to provide with the input and the expected output to our model that we want to fine-tune such that it can correctly understand what are these corresponding outputs, and the next time we provide a question, it will be able to provide the right answer. So we are supervising the process by providing these expected outputs that will supervise the model. It's pretty much like when we have in traditional machine learning features that are representing the X and then the corresponding Y, which is our dependent variable that corresponds to each of these observations. So we know for a set of features what is the corresponding response variable's value. In the same way, we have this input and the corresponding output, and this output will then supervise the training process during this fine-tuning stage. Because fine-tuning is nothing but just a second layer of training of the pre-trained large language model. Let's now talk about another type of fine-tuning technique, which is the self-supervised fine-tuning. So this is an important technique that is in short called SSFT. And this method is quite powerful and interesting because it doesn't rely on a labeled data like the supervised fine-tuning does. Instead, it uses unlabeled data to improve a model's language understanding and generation capabilities. So the SSFT works similarly to how the foundation large language models are trained. The key idea here is to leverage the vast amount of unlabeled text data that is available there and contains a lot of good information. So imagine you are reading a book and you are trying to guess what the next word will be. By consistently making these predictions of this next word, you will then get a better idea and better understanding of the language. This is essentially what the SSFT does. So the way it works is that it first takes this large corpus of text, and then the next thing it does is that the model is trained in a self-supervised manner, meaning it learns to predict the parts of the text based on other parts. It doesn't use labels to supervise the training. It does everything by itself, hence the name self-supervised. So it's supervising itself by looking at other parts of the text. For example, if you feed to the model and the sun rises then the model will accurately predict that the next word should be the east. So then the entire sentence would become the sun rises in the east. By doing this repeatedly with huge amounts of text, the model learns the structure and the patterns of the language. So the SSFT, or the self-supervised fine-tuning, is incredibly useful because it doesn't require this time-consuming and expensive process of labeling data. So we just saw that in case of supervised learning, supervised fine-tuning, we need to put our data into the specific format. First, we need to collect the data and then set it in this format of input and then output and then validate that the data is accurate. Especially if we want a larger data for the fine-tuning, that task can very quickly become a resource-heavy task and also expensive one. Instead, what we can do is that we can utilize the existing text that we have available, which contains a lot of useful information, and we then no longer need to spend our time on labeling the data. So this process is then much more scalable. We don't need to label every time the data. Instead, in a scalable way, we can fine-tune the model, and this is also an efficient method for improving this general language understanding and generation of this text. This approach allows us to fine-tune the model to align with specific applications by curating this training corpus accordingly. So, just to sum up, the self-supervised fine-tuning, the SSFT, is a fantastic approach for enhancing a model's language skills without the need for the labeled data, unlike the supervised fine-tuning does. And by predicting the parts of the data based on other parts, the model becomes better at understanding and generating language. This technique is invaluable for the tasks like language modeling, where the ability to predict and generate coherent text is really important. Hi there and welcome back. Now let's dive into another interesting and popular fine-tuning approach called reinforcement learning with human feedback, or RLHF. So this one is used for fine-tuning by many cutting-edge tech companies, including OpenAI, to fine-tune their generative AI models, including the GPT-4 and GPT-4.0 recently released. So this method uses the human feedback to guide the model's learning process, aligning it with human preferences and improving its performance on various tasks. So the intuition behind the RLHF, so the reinforcement learning with human feedback, is the following. The core idea of this technique, this fine-tuning technique, is to have human reviewers to evaluate the quality of the model's outputs. Their feedback is then used to adjust the model's behavior, making it more aligned with what humans consider to be good or useful response. This approach is particularly valuable for the tasks that require a high degree of safety, accuracy, and user satisfaction. So, when it comes to the reinforcement learning with human feedback, this technique is where humans help to improve the AI by giving the feedback on its responses. So, this feedback guides then the model to generate better, more accurate, and safer answers. First of all, the RLHF helps to make the conversations engaging and informative. So here the goal is to make AI responses engaging and highly informative. The process is that the human reviewers will then rate the AI responses based on how interesting and informative they are. The feedback then helps the model to produce better conversations over time. And the AI becomes excellent at having natural, engaging conversations that users love. Another benefit of RLHF is that it ensures that the answers are accurate. So it ensures that the AI gives accurate and helpful answers. The reviewers check the AI's responses for the correctiveness and the relevance. Their feedback is then being used to fine-tune the model. So in this way, the generative AI model is improving itself by providing more and more precise and useful answers to the user, boosting the user trust. So next, let's discuss very quickly about following the instructions safely and correctly. So having the AI following user instructions accurately and safely, the human feedback then teaches the AI to follow certain directions precisely, assuming that then the humans will provide this safe and accurate instructions. So reviewers ensure that the model adheres to the instructions and performs the tasks safely. And the outcome is that the AI model becomes reliable in executing tasks exactly as instructed, enhancing the safety and accuracy. There is, however, a drawback here because if the intention of the reviewer is a bad one, then the model will also become inherently unsafe. Therefore, it's really important to know the reviewers, to select them, and to ensure that they are not on the wrong side of the story. So another thing that I didn't mention here on the slide specifically, but I still wanted to mention, is performing the specific tasks. So this enables the AI to carry out specific tasks as instructed, this specific fine-tuning approach. So reviewers provide feedback on how well the AI performs these tasks, and this helps the model to learn the correct way to execute them. So, by using this reinforcement learning with human feedback, the AI gets better at understanding and performing these different sorts of tasks, making it more versatile and useful. So, human feedback is really important because it helps to align the model's performance with the user expectations and also company's expectations. It ensures that the AI outputs are useful, are accurate, and safe. By involving human reviewers, we make continuous improvements to our model's performance. This is just a high-level information, just to keep in mind that the human feedback is really important when it comes to developing and fine-tuning large language models. So, human feedback is key to enhancing generative AI models and applications like the ChatGPT and InstructGPT. So, here's an example of ChatGPT, and here the process of the reviewers would be pretty much the same as you can see on the screen. So providing the instructions, asking what the model should do, and then once the reply is provided, then the human reviewer can evaluate whether this is good, or it needs to improve the prompt, or it needs to provide some better instructions. And that's the idea behind the reinforcement learning with human feedback. So in here you can see that I'm mentioning remove anything that might sound wrong or that might be just too much in the professional setting, and be professional. So in this way, I'm making the model to be more accurate, to not provide unprofessional language, and to ensure that this is just not too much. And you can see that here I'm also providing more improvement points, saying improve your tone, you are too formal. So kind of helping the model to understand this middle ground between too formal and informal. So the same also holds in the InstructGPT. This is, by the way, from the OpenAI's official website describing the InstructGPT. And the OpenAI is integrating this idea of reinforcement learning with human feedback heavily, both in ChatGPT and in this InstructGPT. And by integrating human insights, they ensure that the models that they have can engage in meaningful conversations, providing accurate information, and also they follow instructions that the company is providing. Of course, here we are assuming that the company is providing accurate instructions to ensure that everything goes according to the safety guidelines and according to the law. So here is a simplified process of how reinforcement learning with human feedback is applied. First up, we have the supervised fine-tuning. This process begins with supervised fine-tuning, something that we just discussed, where the model is trained using a curated, this collected dataset that consists of input-output pairs. This helps the model to learn from examples. The next step is to train a reward model. So human reviewers evaluate the outputs that are generated by the model from the previous step, and then they are ranking these outputs from worst to best. This ranking is then used to train a reward model, which then assigns scores to the quality of the model's responses. Obviously, the ones with high quality will then get so-called candy, so they will get a high score, versus the ones of bad quality will get a low score. So in this way, we can then teach to the model what is right and what is wrong. Next, what we have is the third step, which is the reinforcement learning. So the fine-tuned model is then further optimized using this reinforcement learning algorithm. So here we can use things like the proximal policy optimization, the PPO, and this is a common policy that is used also across many cutting-edge tech companies. And the idea is that the model will then provide feedback to be fine-tuned, guiding it to improve its performance continuously. So it will continuously improve the model performance. So reinforcement learning with PPO, this proximal policy optimization, involves these 3 to 4 steps that we'll go in a bit. And there's several steps where a model learns from interactions with an environment using this feedback to improve its performance. So next up, we have the reinforcement learning. The fine-tuned model is further optimized using a reinforcement learning algorithm such as the proximal policy optimization, or the PPO. So PPO is a popular reinforcement algorithm that is also used as the fundamental part of the fine-tuning process by cutting-edge companies like the OpenAI to optimize the model. The reward model provides this feedback to the fine-tuned model, guiding it to improve its performance continuously. So think about every time when the model is doing something and human evaluator provides a score, so saying this is a good answer, this is a bad answer, then this feedback is being used as part of the reinforcement learning to then in the next step improve the accuracy of the model. Pretty much like the in case of the boosting algorithms, when the model continuously assesses where the model was able to accurately predict the classes and where not, and then it would also focus on improving those incorrectly classified observations. So in this way, the model can continuously improve itself. The reinforcement learning with PPO, or the proximal policy optimization, involves several steps where a model learns from the interactions with an environment, using this feedback, these scores, to improve its performance. So here is how it works in more detail. First, we have the prompt. The process starts with this prompt or an input to the model. Then we have the model response. So the model generates a response based on the prompt. Then this response is evaluated by a reward model, which assigns a score based on the quality of the response. And then in the final step, we have the PPO algorithm, the proximal policy optimization algorithm, which is used to adjust the model based on the feedback from the reward model, optimizing its parameters to improve these future responses. So you can see that with these arrows, once we go on to the reinforcement learning algorithm, it provides us a feedback, and this feedback is then going back into the model, and then it improves itself every time. So this is basically the high-level idea of the reinforcement learning with human feedback. As you can imagine, this is much more powerful as a fine-tuning technique than just the supervised fine-tuning, which on itself can be used as a separate type of fine-tuning technique. But when you have the reinforcement learning with human feedback, you are adding this extra layer of quality on your fine-tuning process, because then you are involving human feedback and human reviewers that can help to improve the model's accuracy and ensure that the model outputs are relevant, are accurate, and they are safe. Let us actually consider an example where the goal is to fine-tune a chatbot to provide helpful customer support responses. So first up, we have the prompt. And the prompt says, how do I reset my password? Next up, we need to provide this to the model such that the chatbot can generate a response. So next step, the chatbot generates a response. For example, it can be, you can reset your password by going to the account settings page. Then next up, we have our reward model, the chatbot that generated this. Next up, the human reviewers evaluate this response. They consider the factors like accuracy, helpfulness, clarity, safety, and suppose they score this answer that was provided by the chatbot 8 out of 10. So this for being accurate and clear, but still missing some steps and some important information. So next up, the scores from the human reviewers, this 8 out of 10, are used to train this reward model. This model learns to predict the quality of the responses based on the feedback it received. So based on the feedback that this response is 8 out of 10, then this reward model will be then understanding what kind of information it needs to provide next time. So how it can fix the model. Then the scores, this 8 out of 10 that was assigned by the human reviewer, is used to train this reward model. This model learns to predict the quality of responses based on the feedback it receives. So next up, we have the reinforcement learning with the PPO. So the PPO algorithm is applied to optimize the chatbot's responses. And here is how it works in more detail. So first up, the model generates several possible responses to the same prompt. The prompt where we were asking, how do I reset my password? So next, we need to do the evaluation and ranking. These responses are ranked by the reward model from the best to worst. So once the training of the reward model is done, next up we need to perform the reinforcement learning with our PPO. For example, the PPO algorithm is then applied to optimize our customer support chatbot's responses. And the first thing that it will do is that the model generates several possible responses to the same prompt that we provided. So how do I reset my password? This was the prompt. Then what the model needs to do is to evaluate and rank. These responses are then ranked by the reward model from the best to worst. So basically, it generates the multiple responses, and then in this step, we are evaluating these multiple responses and we are ranking them from the best to the worst. Then the feedback is used to adjust the model's parameters, nudging it towards generating higher quality responses in the next steps in the future. For example, the model might generate additional responses like you can reset your password by clicking on Forgot Password or on the login page. Or another one can be to reset your password, visit the account settings, click on Security, and then reset your password. The reward model will then score these responses, and the PPO algorithm updates the model to favor the responses similar to the highest scoring ones. So, as you might have already guessed, this is a much more sophisticated approach to fine-tune your large language model. And it is almost guaranteed that this one will be much better if your human reviewers are doing their work in a proper way compared to just plain supervised fine-tuning. So you might be wondering, but why to use exactly this PPO, this proximal policy optimization? We won't be diving in too much into this as this is out of the scope of our LLM course, but this is an important algorithm, reinforcement algorithm, just to be aware of. And if you are interested, also you can check our reinforcement learning content. So why we use the PPO, the proximal policy optimization? PPO is preferred because it strikes this right balance between the exploration and exploitation, ensuring that the model tries new responses while improving based on the past feedback. It adjusts the model gradually, preventing the drastic changes that might degrade the performance of the model. So reinforcement learning with PPO is quite powerful, and it is using this detailed human feedback, and it is systematically optimizing the algorithm and the model performance. By iterating through these different prompts and the corresponding responses, the feedback loops, and then continuously ranking, evaluating these answers, and then re-ranking them, in this way the model is continuously improving itself. And this feedback loop is very important. And this then ensures that the model is becoming more aligned with the human preferences and expectations. So this one is a really powerful technique, and the reinforcement learning with human feedback as a fine-tuning approach is also a very powerful technique for aligning the models with human preferences. It enhances the ability of the model to generate accurate, helpful, and safe responses by leveraging human judgment to refine and improve the model's behavior continuously.